The subsystem our group chose for this group project assignment is a thermal protection tile. And the goal of the study is to analyze the stresses that act on an individual Li 900 thermal protection tile. And as the space shuttle re-enters the atmosphere, its Li 900 thermal protection tiles protect the vehicle against high temperatures. And upon re-entry, there's a distributed load along the exposed face of each tile on the shuttle. So some background on these thermal protection tiles is they're used and composed of a material called Li 900. These tiles are built from 99.9% pure silica glass fibers and use a high temperature reusable surface insulation. And they are located mainly on the bottom of the shuttle and were used when re-entry temperatures did not exceed 1260 degrees Celsius. The tiles are epoxied to the underside of the vehicle to protect other materials from heat stresses, and they are positioned to protect the hottest areas, mainly the leading face, during re-entry. These tiles are also reusable and are able to be replaced if needed.
In order to analyze the subsystem, several assumptions have to be made about the material. The first assumption is that the subsystem is a thin plate with a normal vector parallel to the z-axis and oriented in the ram direction. The second assumption is that the material is isotropic and all material properties are constant throughout the plate. This allows for the use of the idealized constitutive equation to analyze stress. The system is analyzed at an altitude of 80 kilometers with a velocity of 7 kilometers per second to imitate re-entry conditions. From this, drag force per area can be calculated to assign a traction to the face of the plate. The temperature gradient in the material is 943.5 degrees Celsius, which allows for re-entry temperatures on the face of the plate and an optimal temperature on the epoxied side. Stresses due to temperature and the axial load will be explored further in this study. The tile is set in a series with other tiles and epoxied on the bottom. This prevents movement of the tile in all directions but the positive Z. The traction imposed by drag acts axially on the plate with no shear component as the face of the plate is in the ram direction.
Assuming the only known traction in the Z direction is the air-resistant force on the tiles, so we get the equation as shown. Thus, we have the boundary condition of sigma zz equals to negative drag over area in the zz direction. Assuming there is no body forces, and also assuming each tile experiences the same strain and stress, thus the linear momentum equations are conserved and is satisfied. To find the stress components, we can use the constitutive equations as shown. Subbing into the known values obtained from relevant literatures, we can get the values for each stress components. To simplify the calculations, we can assume K and gamma as the equation shown on the left. Thus, we can get the sigma XX, YY, and ZZ relation as shown on the right side. Since we know sigma ZZ equals to negative drag force over area, we can sub in and obtain the values for epsilon ZZ as shown. Plugging in epsilon ZZ values obtained from last slide into sigma XX, YY, and ZZ, we get numerical values for sigma XX, YY, and ZZ as shown. Thus, the stress matrix is as shown below. We can see each components are negative, and thus each component is in compression.
So our calculated force of drag was about 12 newtons, which we first thought sounded pretty small, but it sounds a lot more reasonable when also considering that we were finding drag way up at 80 kilometers in altitude and that each tile is pretty tiny at only 6 by 6 inches. If you divide that drag force by the area of the tile, we found that the axial stress in the ZZ direction is about 529 pascals. In the stress tensor, this value is negative because the drag force is compressing the tile. The distributed load is also assumed to be perfectly normal to the tile, so there is no stress due to drag in the X or Y directions. The only stress in the X and Y directions is going to be due to thermal stress. In addition to the axial loading, we are talking about reentry, so there's also a great deal of heating due to friction that has to be considered when calculating the stresses in the tile. And in solving this problem, we assume that the tiles were unable to expand laterally in the x or y directions. This means that there is no strain in these directions. When taking these assumptions into account, we found the axial stresses in the x and y to be about 5,511 pascals. This is quite large relative to sigma zz, which makes sense because when the tile is unable to expand laterally, stress it really starts to build up. All right, moving on to critical points of failure. Whether or not our tile will fail can theoretically be determined using the von Mises and Tresca criteria. Using the axial stresses in the tile, both methods result in 6,040 pascals. However, we were unable to find a yield stress for the LI 900 thermal protection tile in the available research papers that we used for the rest of this project. So as a result, we don't know whether or not 6,040 pascals will cause the tile to fail or not. All right, and then finally, this is the poster that summarizes our findings. The first picture is of the Space Shuttle Discovery, which the LI 900 tile was designed for. Underneath that, and in blue, we have all the values that we used in conjunction with the constitutive equation to find the stress state of the tile. And underneath that and to the left, we have all the assumptions that were made in solving this problem. These might look familiar as they were all addressed earlier. And finally, to the right of that, we have the final results of our findings. Assuming no shear stress, we found the axial loads on the tile to be 5,510.8 pascals of compression in the x and y directions and 529.15 pascals of compression in the z direction.